Hi everyone, I'm Mark, and this is my project on Monte Carlo Tree Search for chess. So I'll go over some prerequisite information before I dive more into what I actually did here, starting with what makes chess an interesting problem for AI. Chess is a game of complex strategy with a complicated win condition. Its state space is finite but enormous. Online I found an estimated 10 to the 46 possible positions. Position evaluation needs to consider a wide array of different factors, and this quickly takes up available compute resources. What is Monte Carlo Tree Search itself? Monte Carlo Tree Search is a search algorithm used in decision-making processes which incrementally builds a search tree and estimates the quality of moves by simulating the game from that point on. It balances the exploration of new moves with the exploitation of known good ones, and prioritizes computational memory resources towards highest potential branches of the tree, the ones that are most likely to result in a good move. It has four main phases of its process. Selection, a move with a high win rate, so one that is known to be good, or one that has not been explored much, is chosen. Expansion, child nodes representing future game states from the selected node are created. Simulation, the potential of new nodes is assessed by playing out the game to a predefined depth. And backpropagation, the results of the simulation are backpropagated from the leaf to the root of the tree. Ultimately, the best performing child node is returned. So getting started here, for this project, I wanted to see how well purely heuristic-driven MCTS would perform. So for context, this means there's no opening book, neural network, or other factors influencing the AI's decisions. Moves are picked purely as a result of state evaluation. I expected to mainly have to focus on managing breadth versus depth in the search, resource constraints, guiding the algorithm with domain knowledge and heuristics, and the complicated win state of the game. Checkmate has a lot of factors going on. I expected the AI to have some difficulty with that. Python I specifically chose for its rich library and simple syntax, specifically Python chess to handle game rules and logic. Initially going in, I wanted to implement my own chess game, but I quickly realized that I'd be better off spending my time focusing on the AI itself. To get started, I created a two-player command line chess game, which I ultimately upgraded to be the player versus an AI, and then for testing the AI versus the AI. Implementing MCTS, I established a node class to represent states within the tree, and I created a main MCTS function to manage the search process. I also created a function for each of the main phases. I then added an evaluate state function that runs post-simulation. This assigns values to moves that lead to better game states or worse ones. Initial implementation prioritized moves that led to checkmate. By this I mean I literally just had to say, okay, checkmate is good and you should do anything to get there. It did not even care who was actually winning. Once I saw that the AI was able to actually end games, I then changed it to having it push for a win for itself, and it was actually still able to end games. It just took maybe double the move count. I continued on enhancing state evaluation. So as I said on the last slide, it was pushing for checkmate, ignoring everything else, piece captures, its own safety, its own positioning, which would never work against an experienced opponent. Basic chess tactics were added to the evaluation at this point. So I provided bonuses for placing your opponent in check or capturing their pieces, and added a penalty for being placed in check or losing your piece. These changes help the AI to perform well against chess.com bots. Up in the top right, if you're familiar with Martin, he's kind of like the training bot of chess.com. So I was manually playing against him using my AI's moves. It didn't actually win per se, but it was kind of succeeded in taking key pieces and pushing Martin into a corner. So at this point, I decided to set myself a higher goal, beating Stockfish on the lowest difficulty. And I created a new Python file to manage this that would just run my simulation against Stockfish. Okay, so I then focused on threats and board control. So I looped over the board game grid to analyze the current state, different aspects of it. I added a scoring system to evaluate state to encourage the AI to maintain control over the center of the board. Specifically, I added small point adjustments to controlling the 4 center squares and the squares around those. I also penalized having your pieces be threatened by the opponent and encouraged protecting your allied pieces. One of the actually later things I did, not quite at this point in the development process, was attempting to direct the expansion, prioritizing moving currently threatened pieces as I was noticing, it would kind of leave pieces hanging and not really notice that a move by the opponent had left them exposed. This I'm not quite sure really worked, is why I say attempted. I think it actually ended up kind of making performance overall a little bit worse, unfortunately. Some of the last changes I really focused on were mobility and king safety. So I created helper functions here to analyze the pawn structure, piece mobility, and king safety. I prioritized moves that opened up greatest number of new moves. The reason for this was I kept seeing silly one square over moves, like it would move the rook one square over, or the king or the queen one square over, and it wouldn't really be advantageous. This way, I kind of was hoping to have them actually put pieces in a position that would, actually be beneficial. It did lead to somewhat funny behavior where it kept rocketing the queen to the center of the board type of thing. I think it was seeing like, oh, okay, if I put the queen in the center of the board, I'll get a big point bonus, but that's a terrible place for the queen to be. You want your queen to be safe, so I had to kind of adjust the threat evaluation accordingly there. And this was kind of something that was happening back and forth throughout the entire process. Was as I changed the state evaluation in one way, I needed to kind of shift it, rein it in somewhere else. It was kind of a push and pull of making sure that everything continued doing what it was supposed to. In terms of the other two functions, I provided bonuses for keeping the king in safer ranks and files, like along the edge of the board, ideally behind pawn shields when possible. And I tried to prevent isolated or double pawns with small score adjustments there. The overall result is that Stockfish was very safe. Despite the improvements I made, the AI was not able to secure a win against Stockfish. However, some later iterations were able to draw against the engine with some consistency. I say some later iterations because, as I mentioned, I think I kind of made performance a little bit worse with one of my last changes. But at one point, I ran like 5 simulations at once, and I think 4 of them ended up in my AI drawing against Stockfish, which I'm actually pretty happy with. Can it beat human players? 5 people graciously agreed to play against this, and overall, the AI lost 3 games, drew 1 by stalemate, and it actually won once, which I was quite happy to see. So I'll just play a little bit of this. It can be difficult to kind of tell what exactly the AI is trying to do, but we can see it makes some moves with the intention of controlling center squares and opening up new moves. Admittedly, it probably would benefit greatly from an opening book to help it get its pieces out, though. So we'll just move on here. Okay, so limits of heuristic MCTS. So despite some level of success here, I ultimately think that purely heuristic-based MCTS is not well suited for the game. Logical decisions require heavy state evaluation and quickly take up available compute resources, and manually defining everything required for suitable state evaluation would be both incredibly verbose code and require massive game knowledge beyond my own personal understanding. Combining MCTS with machine learning techniques or just taking an ML approach from the get-go might ultimately have better results. This is actually reflected in most modern chess research as well, which has shifted from heuristic-based evaluations to adopting machine learning techniques, enabling deeper and more nuanced understanding of the game. The machine learning-based models can just pick up on moves that state evaluation just doesn't seem to be able to understand. My overall conclusion, I think this project taught me a lot about both MCTS and performing state evaluation. Admittedly, while I was implementing this, I focused very heavily on the state evaluation, perhaps a little bit too much. Were I to continue working on this, I'd probably focus more on the constructed MCTS tree itself. I think it'd be interesting to see what level the tree fully expands to, where it starts focusing on good branches, and what depth those branches actually reach. In addition to being really interesting, adjustments based on these factors could significantly increase the overall performance. It was really cool to see my AI evolve from a glorified random move generator, which is more or less what it was at the start, to something actually capable of sometimes making intelligent decisions.